Good afternoon, everybody. We will continue to talk about the parts of HPLC instrument. If you remember, we started to talk about the mobile phase, then the pump, and now we will talk about the injector. The injector is the part in which we introduce the sample. We have either automated injector, we call it auto sampler, or a manual one, we call it Ryodyne injector. So we will discuss just the manual one that you can see here. We have two modes of the injector. The one it is titled with inject, the other one is load. In inject mode, we introduce the sample, and we have here a loop that the solution of the sample will fill the loop and the rest of the solution will be discarded. And once we select load mode here, the mobile phase will carry the sample with its analytes and takes it to the column in order to be separated there. The same procedure will be achieved to the reference material, I mean the standard. So once we inject the sample by certain syringes, and here the standard material will again fill the same volume here, so the volume will be kept constant. So there is no variation due to the volume, and instead the variation of the peak area will be just for the real content of the sample in the mobile phase, reflecting the concentration of the material. The autosampler more or less has the same idea, but by using certain robots. Also, we have HPLC columns. Honestly, we don't fill the column by ourselves. Instead, there are some well-known companies we can purchase these columns from, and the technology of these columns is not primitive. Honestly, it is highly tech procedures that the particle bed should be filled in a way that avoid any possible cracks or large void volume, or even badly distributed bed. So this cannot be achieved by simple filling. It should be occurred by using highly sophisticated instrumentation and pumps, and this cannot be simply done manually. It should be done by some well-equipped companies like Hychrome company. And as you know that the distribution of the particles should be even in order to avoid any possible peak broadening and bad resolution due to multipath effect and other Van Demeter parameters. Now we will discuss the detectors, and we will start to talk about the most universal detector in HPLC nowadays is a UV detector. Now, some countries, the most common detector is mass. We will discuss it later, but in our home, the major one used in HPLC instrumentation is UV. As you know, the compound should be chromophoric compound in order to be detected by UV. Simply that the compound should be electronically conjugated compound. This kind of compound can be detected by UV due to its capability in absorbing light. UV part of HPLC simply that we have deuterium lamp, and deuterium lamp radiate a beam of light which can be resolved by some monochromators such as prisms or gratings. Now the selected beam with certain wavelength will pass the cell of the UV, which contain some mobile phase components such as analytes. If we have light absorbing analytes, then the wavelength beam will be partially absorbed, and the detector can measure the degree of this absorbance by some electrical circuits converting the light language to the electricity language. So UV should be just reserved for conjugated compounds that contains, for example, benzene or any other benzoid parts. Now, one of the UV technologies, we call it photodiode array. It is still UV detector, but the idea of photodiode array that you can monitor the chromatogram of your sample with almost the whole range of UV and even visible light. So from 200 nanometer to 800 nanometer can be monitored by just a few seconds of detection. So it is very useful to make sure that if you have a compound with certain signal, that there is no hidden signal for any contaminant co-eluted with your sample, and the same thing that we can get more data rich chromatogram having retention time as a vector, absorptivity or the intensity of the peak as another vector, and thirdly the wavelength as another dimension. So the idea of photodiode array, that the light source, usually the deuterium lamp, will radiate certain range of radiation, usually from 200 to 800 if we need UV and visible, that the holistic beam will pass the sample, and the sample here can take the part of the light matches its electronic conjugation. You can think of it simply like if you have analyte and you have UV spectrum. So UV spectrum will depict that the sample absorb certain wavelengths of light, not the whole range. The same idea that the analyte here in just millisecond will absorb what it needs from the whole light radiated from the light source, and the rest of light will be resolved afterwards by some monochromators such as prism or gratings. And usually, to be honest, we use gratings to gain better resolution. You can think of gratings as a computer CD. You can see that computer CD gives rise some rainbow colors because it has the capability to resolve light. The same thing, we use gratings here to resolve light, and each light beam with certain wavelength will be measured by a diode. So the idea that we gain here all the absorbance beams with referring to whole UV and visible range, and this is one of the good technologies because we have so many data gained by these diodes. We call this part diode array because we have array of diodes. These data will be further manipulated by mathematical Fourier transformation in order to convert sinusoidal function, like sine function of the wave here, to just a signal. And in this case, we can manipulate the data properly.